Hello, and welcome to this video on concave lenses and magnification, where we will talk about how to draw ray diagrams with concave lenses, what type of image is formed by a concave lens, and how to calculate magnification. Refraction happens when light travels from one medium into another, for example air into glass. As the light reaches the boundary between the two mediums, it changes speed, and when the speed changes, so does the direction of the light. When the light moves from air into glass, it slows down and bends towards the normal. When the light moves from glass into air, it speeds up and bends away from the normal. There are two types of lens that you need to know about, convex and concave. They both refract light, but in different ways. Convex lenses converge light at a focal point, or a principal focus. Concave lenses diverge the light. To find the focal point, backtrack to where the diverged rays appear to have come from. There are key terms that you need to know about lenses. The lens axis is a line passing through the centre of the lens. The principal focus, this is the point where the parallel rays of light will converge. The focal length, this is the distance between the principal focus and the lens axis. There is a principal focus on both sides of the lens, and they will have the same focal length. Accurate ray diagrams need to be drawn to scale on graph or squared paper with a pencil and ruler. My scale is 1 square to 1 centimetre, so the focal length is 4 centimetres, 4 squares, and the object height is 3 centimetres, 3 squares. To draw the accurate ray diagram, first, draw a line from the top of the object to the lens axis. This line should be parallel with the principal axis. 2. Refract the line so that it appears to come from the principal focus. The ray that extends back is a virtual ray and should be dotted. 3. Draw a second line from the top of the object that goes through the point where the lens axis and the principal axis meet. The image is formed where the virtual ray and the real ray coming from the top of the object and going through the principal axis and the lens axis cross over. This image is the right way up, it is smaller than the object, and it is a virtual image as it is made from at least one virtual ray. Things to note on this particular diagram are that the rays do not have to actually go through the picture of the lens. The lens is just a picture. It is important that the first ray is parallel to the principal axis and then refracts when it gets to the lens axis. It is not important that it actually goes through the picture of the lens. You also may not actually get a picture of the lens on the diagram. It may be the symbol for the concave lens. And the symbol for a concave lens is a line with arrows on either side of the line, but the arrows are pointing inwards, not outwards. Ray diagrams for concave and convex lenses have some things in common. The principal axis is the axis that the principal focus is on. F is one focal length from the lens axis. And 2f is twice the focal length from the lens axis. With convex lenses, depending on where the object is, depends on the type of image that you get. With concave lenses, no matter where your object is, your image will always be smaller, upright, and virtual. It may be necessary to compare concave and convex lenses. Their similarities are they both have a principal focus on either side of the lens at the same distance away from the lens axis. They also both refract light. In a convex lens, light that hits the lens parallel to the principal axis converges at the principal focus on the second side of the lens. It can produce real and virtual images depending on the position of the object in relation to the principal focus. In a concave lens, light that hits the lens parallel to the principal axis diverges, but appears to come from the principal focus on the same side as the incident light. It only produces virtual images that are upright, smaller than the object, and on the same side of the lens as the object. The magnification of a lens can be calculated using the following equation. Magnification equals image height divided by the object height. There are no units for magnification as you are dividing height by height, but you will need to make sure that the units for height are the same, either both metres or both centimetres. The information to calculate the magnification can be measured from an accurately drawn ray diagram that has been drawn to scale. Here's an example. So here we have an accurately drawn ray diagram, and the scale is 1 square is 1 centimetre. So we have 5.5 centimetres for the image height and 3 centimetres for the object height. If we substitute that into our equation, we have 5.5 divided by 3.0, and that gives us a magnification of 1.83. And that's the end of this video. Thank you for listening.